So this is a sort of optimization question. We've got two variables. We've got a constraint that our solutions have to satisfy, which restricts our solutions to being inside the disk, right? So we've got sort of two regions. We've got the region where the x squared plus y squared adds up to 1. Right, so that's the circle. And then we've got the interior of the circle where x squared plus y squared is less than 1. Okay, so I'm going to name those the interior and the boundary. And these two regions require separate techniques for maximization. Okay? So in one variable, right, we have to find critical points and then test our endpoints, right? So in two variables, our endpoints are going to be this boundary here. Right? We'll look at what's going on when x squared plus y squared is 1. So there's two parts to the optimization here. The first part, the interior part. Happen on the interior. To analyze what goes on in the interior, we find critical points. So we want to find when both of these partials are 0. That'll be a place where our tangent plane is horizontal. Found a critical point, and we're going to check that that critical point lives inside the disk. We plug it into the equation for the interior, get a quarter, so it's inside. Okay, now that we've got the critical point, we'll do sort of a Hessian calculation for it. So we'll take our second derivatives. We get a constant Hessian everywhere. Our second derivative test tells us that this is a minimum. So there's a critical point inside the disk. Okay, now we'll see what happens on the boundary of the disk. So that is when we have an equality in our constraint. We've got a thing that we could use to set up Lagrange multipliers. Rewrite our constraint to be equal to 0. For Lagrange multipliers, we want that the gradient f is parallel to the gradient of g. So we want that this circle is tangent to the level curves. Okay, so gradient f is there. Rewrite that statement about equality okay, now we want the points that satisfy this guy. Right, so when we see an equation like this where we've got 2y on both sides, or something equals something times lambda, right, we can use this to break into some cases. Let's say this in the order, if y is not 0, then we get lambda equals 1. If y equals 0, we don't know about lambda. Okay, so let's treat both of those. So plugging that into our top equation now. We can solve and get x is -1. So now we found a potential critical point. So we start off with x is -1, plug it in here, that forces y to be 0. So we get a critical point. And then going the other way, so we've used up this hypothesis, right? We saw what critical point that gives us. So we get two options for x. Now we get a couple new critical points. Okay, so now that we've got these results from method of Lagrange multipliers, now we have to plug them in and see which one is bigger, which one's smaller, etc. So so now we're on our last step of minimization and maximization. Okay, so we'll plug in 1, you get 4. Plug in -1, 0. Okay, and we plug in the critical point that we found here, and we get what will it give us? It'll give us -1/2. Very good. So now we've got sort of 3 values, and we'll say which one's min, which one's max, etc. Yes?
When we take lambda equal to 1, don't you assume that y doesn't equal 0?
Right. So, okay, so if we start off with this hypothesis, right, yeah, we're sort of dividing by y there. We still get y equals 0. Huh. Right, so we start off, we say, if this is 1, then we solve for x, and that value of x forces y to be 0. Yeah, so I guess you're right that you've got this contradiction, right? You say y is not 0, and then you conclude that y must be 0, right? So there's a sort of proof by contradiction there, and that's, I guess, why this critical point doesn't come up. Yeah?
Is that a contradiction though, because the conclusions are either lambda is equal to 1 and y can be any value, or y is equal to 0 and lambda can be any value.
Uh-huh. Oh, so you're saying that we have to be in this conclusion, but this one's kind of...
Like, it's not an either or, it's an or, right? So it can be both.
Ah, yes, okay, yeah, good. Yeah, this isn't exclusive. Okay. Nice. Other questions or thoughts there? Yep.
Okay, so the first part, we just find the parts where the partial derivatives are equal to 0, and then we use the Hessian matrix to check whether that's a maximum or a minimum, right?
Yeah.
So that's for one of the critical points, and then we find other critical points with the
Lagrange thing?
second part of the lump stuff. But what's the, like, I don't understand the reason why the Lagrange part works.
Right, okay, so I should sort of say how this relates to the situation in one variable. Right, so let's take a step back to first year for a moment, and we'll think about how optimization went in that context. So in first year, we'd have these functions, usually on some interval, right? And we would find their critical points. And to maximize or minimize, we'd find the critical points and then plug in the boundary points. So okay, so that's the story of optimization in one variable. So the reason why we need to do Lagrange in two variables is that here we're optimizing over a region now, right? So we've got some region in the XY plane. And then a graph sitting over top of that region. So we locate our critical points inside the region.
There's only one in this case, right?
Yeah, sorry, this is not a representative picture of that question. So you find your critical points, and then you've also got all of these boundary points to check. Okay, so here we've got our sort of interior critical points, and then we've got our boundary points. So Lagrange is what lets us look at that boundary.
What does it say about the derivative on the boundary?
Right, it says that it's